So hi everyone. Okay, today we'll finish the final main topic of this class, and then for the rest of the next week and a half, I will give a quick introduction on an important topic I skipped, but that since it's just going to be a quick introduction, it's not going to be in the exam. So where were we? So what was left was we just stated the following theorem. So remember, sorry, we had psi, some map from B to BO, and then we defined a map from the nth Bordism group with psi structure to the nth homotopy group of M psi, and this sending phi to the composite. Sorry. That's the fundamental class of our manifold, and that's the map induced by phi on Thom spectra, which I guess I didn't give it a name, but let me call it phi anyway. And psi is an isomorphism. So this essentially reduces the computation of Bordism groups to the computation of some homotopy groups per spectrum, and this is actually how Bordism groups are typically computed, by computing these homotopy groups. And let me state a corollary from these. So let's say X a space, then the psi homology is just the Bordism group of closed N manifolds with psi structure equipped with a map to X. So this gives a complete description of M-psi homology in terms of manifolds. And the proof, I said last time, but let me repeat it, is just the right-hand side is just omega n psi x, where psi x from B times x to B to BO is this composite here. But n psi x is n psi tensor sigma infinity plus x. Oh, sorry. I am trying to put the plus there. And that's just because, you know, it's a colimit of this thing, but I can essentially take first the colimit here and then here. And well, the point is that it's constant in X, this colimit. So I'm just doing tensoring. I'm just tensoring by sigma infinity X plus. Okay. Questions so far? No. So let's prove the theorem. So this is a map of abelian groups, and we want to say it's an isomorphism. We will show that it is injective and surjective. For doing so, we will need a couple of results in differential topology. And the notes you can find, the references and everything, although I probably have to improve them a little bit. Let's see if I can manage to do it today. So the first is this theorem, which we actually could almost prove now, which is the smooth approximation theorem. That says if f m to n is a continuous map of smooth manifolds then F is homotopic to a smooth map. Okay, that's one thing. But moreover, if A inside of M is a closed subset such that F is smooth in a neighborhood of A, we can choose the homotopy relative to A. So if F was already smooth in a neighborhood of some closed subset A, we can not change F on that closed subset, so not on the neighborhood. This is a basic theorem. Essentially, the proof is you embed n into R to the n for some n. You convolve it with some very small bump function so that the image of F still, now F after the convolution is smooth, but the image lives in some tubular neighborhood, and then you project it using the projection of the tubular neighborhood. Okay, this was a very sketch. And okay. Questions about this theorem? The other theorem is harder, although not much harder, is the transversality theorem. Well, okay, it is harder. It's based on a hard result. The proof I have in mind is simple, that's because we are off-sourcing the hardness to a complicated result. So now let F from M to M prime smooth map of smooth manifolds, and n inside of M prime some embedded submanifold. Do I need closed? Yeah, sorry, some compact, no, not closed, but compact embedded submanifold. And just to be clear, if M prime and n have boundary, which will be the case in a step of proof, I'm asking that n is embedded neatly. That is to say that the boundary of n is on the boundary of M prime. Bad. So actually, let me write it neatly embedded. But we defined what neatly means last time. It means that near the points of the boundary, it's just the embedding of a half hyperplane inside a half space. Then a hyperplane, a half subspace into a half space. Then F is homotopic to a map transverse to N. And as before, moreover, if A inside M is a closed subset such that F is transverse to N in a neighborhood of A, we can choose F, the homotopy relative to A as before. And actually, let me remark because this might not be obvious, but certainly F is transverse to N on the points that don't hit N. So in particular, we can choose the homotopy that is constant outside of a neighborhood of N. We can choose the homotopy it's constant of a neighborhood of N. Well, of F inverse N, really. Because, well, again, where F doesn't intersect N, it is certainly transverse. Okay. So I'm stating the general version of this theorem, but for surjectivity, we will need a simpler version of this theorem, but we will need this full general version for the injectivity part. So other questions?
Maybe, do we have this smooth approximation theorem in algebraic geometry as well?
Oh, no, absolutely not. No. This works up to C infinity. The moment in which you get into analytic maps, all bets are off.
Okay.
No. So I'm proving this Pontryagin-Thom theorem, and there is a version of this theorem in algebraic geometry, but it is much harder and it works on in characteristic 0, and it's not quite clear what the statement should be in positive characteristic. It's like literally, there are people working on that like right now in this very moment. It's much harder. This works but this Pontryagin-Thom theorem, perhaps I should also mention, works also for topological manifolds, given the definition properly, but it's a much harder theorem. That's because the notion of topological transversality is extremely subtle. In fact, it's approachable in dimension different from 4, and if I understand correctly, it's also true in dimension 4, but the number of people who understand the proof is very small. So it is a very hard theorem.
Can you recall again what embedded submanifold was?
Oh, so, okay. Submanifold is embedded, or neatly embedded, I guess, in the case where they have manifolds, if locally around every point of N, it looks like, well, either R to the K inside R to the N, or 0 infinity times R to the K minus 1 inside 0 infinity times R to the N minus 1, depending whether the point is a boundary point or so it is X in the interior of N. X is in the boundary of N.
Okay, but this looks very weird to me, the statement then, because then say F is the identity and N is some embedded submanifold, then I have an F which df everywhere has full rank.
Yes, the identity is such an example.
And
The identity
then,
is transverse to every submanifold.
and then, it is transversal already.
Well, yes, remember the definition. So recall, maybe I should recall the definition of transversality. F is transverse to N if for every x in N, f of x in N, we have Tx, the image of these, plus Tf of x n, sorry, not direct sum, just sum, is Tx n prime. It intersects it as small as possible, but of course, if the dimension of M is huge, as small as possible means like it contains it.
Okay, yeah, I thought it was a direct sum.
No, absolutely not. Absolutely
yes,
not.
now it makes sense. Okay, thank you.
Absolutely not. It is a direct sum when well, the dimensions are complementary, because that's probably the case you have in mind. It's not. And note that, for example, if the dimension of Txn is too small, if the dimension of M is too small, it doesn't have enough tangent space to get this condition. Transverse means simply that the image is disjoint from N. That's another important example. Okay. Other questions about this? Because now we're going to prove the surjectivity of this map. So for every class in the homotopy group of M xi, we'll construct a manifold. Okay, so what we have? We have a map like this. Now, remember, we can write this as follows. First, we can write it like this. Sorry, sigma infinity minus n, Thom space of psi n, where psi n from B times BO into BON. So remember, let me draw perhaps a picture. I have BO. Inside here, I have BON sitting, if you want, with the tautological bundle minus n. And here I can take the pullback. And since BO is the colimit of all BON, sorry. I can call this Bn. Since BO is the colimit of BON by descent, if you want, this follows that B is the colimit of the Bn's. And therefore, the Thom spectra can be realized. As so the Thom spectra psi can be realized as the colimit of the Thom spectra of psi n. And now the Thom spectrum of the psi n, I can think of it as sort of the desuspension of the Thom space of the psi n. That's this suspension, by the way, is just this n here that I am removing to get a topological space. Because, you know, if I consider here, I'm taking with Thom space of psi n, I literally mean the Thom space of the pullback of the tautological bundle, which is shifted by n. We need to shift by n to put it in degree 0. Okay? So let's suppose we have this map, what did I call it? F. So first of all, by compactness of the sphere spectrum, F factors through some sigma minus n, sigma infinity tom psi n. That is, we get a map sigma n plus k sphere to sigma infinity tom psi n, which we'll still call F. We have some object here, which is i.e. a class in pi m plus k tom psi n, whose image in pi k tom psi k, sorry, wrong letter. Yeah, I shouldn't use k for this, for this, sorry, n was already, well, okay, hopefully you, I'm sorry, n was already occupied by a different element. Okay, is it clear? So I can lift my class F here to some other class that I still call F here in the stable homotopy groups of this pointed space. But now, tom psi k is a colimit of SKs. Remember how we defined it. Therefore, it's k minus 1 connected. Because now we have a map from the unstable homotopy groups to the stable homotopy groups. Here is our class F. And we know that this is surjective for, now I'm going to screw up the indexing. N plus k lesser or equal than 2k minus 1, I think. Of test k, well, test k plus some kind of constant, which is possibly minus 1, possibly 1. I don't remember, it doesn't matter. But this is the Freudenthal suspension theorem. Okay. So if I take k large enough, F is in the image of, sorry, pi m plus k tom psi k. So to boil down, I have finally constructed a map of pointed spaces, which I'll still call F, that factors of my map like this. So I started with a map like this, and I factored it until I got to this Tom space of this universal bundle. For some k, possibly some big k, but we don't care, some finite k. Is this clear? Okay. If there are no questions, I'll go forward because we need a further reduction. Now recall that BOD was the d-dimensional Grassmannian in R infinity. And so we can write it as the union over M, the Grassmannian in Rm. Or if you want, rather than the union, perhaps we care more about it being the colimit. So now let psi k comma m be, again we take bk times, we restrict it further to this Grassmannian. And let me call this for brevity bk comma m. And now the Tom space of psi k is just the colimit of the Tom space of psi k comma m over m. Okay, why am I doing this? Well, because now this guy has a nice property. This is a compact, this is a closed, actually smooth manifold. I should have remarked it when we discussed Grassmannians, but I gave you an atlas, some explicit charts around every point, and I should have remarked it that this was actually a smooth atlas. So this is indeed a closed smooth manifold canonically. And it is, the closedness is just because to get M finite. Because remember, another way of describing these are where orthogonal projections of rank D. And this is easy to see that it is compact. Because yeah, you can just compact because it's closed and lies in, I don't know, the norm is greater than some big M. So this indeed, it's a closed smooth manifold. It's a smooth manifold because I gave you charts back in the day, and they were indeed smooth charts, and it's closed because it's, well, it's compact. So now, okay, again, by finiteness of Sm plus k, we can further restrict f to km for some m. So we have this map. And these, in a very complicated way, maps into omega infinity, sigma, k, and psi. And the composition is the map we started with. And these also maps to the Thom space of these, where this is the tautological bundle on the Grassmannian D-planes in Rm. Okay, and that's the key diagram I want to consider. Why do I want to consider this? Because this Thom space here is almost a smooth manifold. This is the one-point compactification of eta xi m, which is a smooth manifold. It's a vector bundle over the Grassmannian. And okay, I guess you should check that the pre-images of the charts I gave you for the Grassmannian give you charts on this vector bundle, but it's easy. And moreover, eta km contains the Grassmannian as an embedded closed submanifold as the zero section. So now we want just to deploy our theorems. So this, let me call this P, this F, this is PF, to make sure that PF is transverse to the zero section. This is a bit subtle because the Thom space is not a smooth manifold. It is the one-point compactification of a smooth manifold. But it turns out not to be a big deal. So let me explain how to do that. Okay. Is everyone on board?
Okay, just a short question, because maybe I'm a little confused with all the new definitions and indices. So how do you get the last map from the Thom space of theta km to
so yeah, theta kn is a vector bundle over this bkm, which was a pullback. Oh, sorry, to the Grassmannian, right? And this, by definition, is the vector bundle obtained by pullbacks from BOD. Why am I calling it Grassmannian D? It's Grassmannian K, of course. Sorry. Well, it's defined as the pullback of this vector bundle, right?
Yes. And now I was talking about the horizontal map to omega.
Oh, the horizontal map. Okay, this was just a huge composite. So let me write it again. You have this guy maps inside the Thom space of psi k. since this is the colimit of these pieces as m goes to infinity, which maps to, well, omega infinity, sigma infinity, the Thom space of psi k, just by adjunction. And these maps to omega infinity, sigma k, and psi. Because recall, we had a map. So essentially, the idea is we have this huge space here, and we have a class in the homotopy groups of this huge space. We want to reduce and reduce and reduce further until we end up with something which is basically a finite dimensional manifold.
Okay, thanks.
And this is okay. There is the small issue that this is not a finite dimensional manifold, but it's not a big deal. It's only one bad point. So we let U to be PF inverse of this piece. This is in Sm plus k. In fact, it's inside R m plus k inside Sm plus k. And this is an open subset. In particular, it's a smooth manifold. And therefore, up to homotopy, we can assume PF restricted to U from U to eta km is smooth. Now, there is a small issue I am sweeping under the rug here, in that we have to choose the homotopy in such a way that it tends to infinity as the point tends to the boundary of U. But you can do that because you can always choose the homotopy in such a way that it's a small deformation. So if the point here goes to the boundary, this point goes to the boundary here. So this actually extends to a homotopy of the full map on Sm plus k. You just leave it constant the base point on the complement of U. Okay. Oh, good. And now we have these. And so furthermore, we can homotopy further in some to make it transverse to GR KR to the M. And again, since we can just do the homotopy in a neighborhood of the Grassmannian, this is going to stay to extend to a map from the full Sm plus k. Okay, now that we have this, we can take M and define it as the pre-image of the zero section here. And okay, so this is an embedded submanifold of Sm plus k of codimension k. Because the codimension of the Grassmannian inside the vector bundle is exactly k, it's the rank of the vector bundle. Moreover, PF restricted to the normal bundle. So okay, so let nu the normal bundle of M in Sm plus K, then nu. So then, sorry, the differential of PF restricted to nu induces an isomorphism with the normal bundle of the Grassmannian inside the vector bundle, but that's just R K R D into psi K M. Sorry, eta km. Eta km. I'm using eta for the topological bundle on the Grassmannian and xi for the bundle on this pullback thing. But then that's so nu is classified by some vector bundle. So the normal bundle of M therefore is classified by this map. And I want to claim that the fact, sorry, what I want to say, sorry, I have this map to the Grassmannian, Sm plus K, sits inside Sm plus K. I have a community diagram like this, mapping, well, in a very complicated way, all the way to BO, and here I had B. And now remember, this map had a lift here. This map now is, by construction, n minus the tangent bundle of n, because it's the map classifying the normal bundle. And so I get a lift phi here, just by composing F with this map to Sm plus K. And sorry, yeah, I should say Rm plus K. Yeah. Because Sm plus K, of course, mapped only in the Thom space. So the upshot M phi is a manifold with psi, so that was psi structure. Moreover, if you look at the construction we used, the composite should perhaps some space of nu, which is m minus Tn up to m psi, is exactly our original F. I'm sorry, this cannot be Rn. What do I want to say? Oh, you. That's the point. The open that mapped to my piece. Sorry. Okay. Questions? This is really not a hard proof, but it might be a bit fiddly if you've never seen it before, because you have many indices to keep track of it, but essentially none of them does really anything. The proof of surjectivity, unfortunately, it's similar but more complicated. So let me, what time is it? Yeah, I think I have time to explain it. But before I go to the proof of of injectivity, is the proof of surjectivity clear? So actually, let me review it. So we start with a map like this. The point is that this m psi can be written as a big co-limit in the end of this Thom space of psi k comma m. And that plus the Freudenthal suspension theorem essentially tells you that this map factors through one of those. At which point, to get you have a map to this, which is the 1-point compactification of eta km of a smooth manifold. You want to obtain your manifold by just taking the intersection with the zero section of your map. Now, this in general will produce something horrific. So you have to homotopy stuff a bit until you become transverse. And by the way, this is the hard part in a topological case. The rest is kind of formal. And after that is transverse, well, the normal bundle is exactly obtained as a pullback of the normal bundle of the zero section here. And so it has a psi structure because we constructed in such a way that we have given a lift to this psi km. In fact, I should have probably defined U as F inverse of psi km. I mean, it's the same thing, of course, but maybe this was made it clear that the map from U to the Grassmannian lifts to this bkm. And then it's just a matter of checking that the definition we gave makes sense, but it does. Because we rigged up everything so that it works. Okay. So the proofs for homotopy, for injectivity is basically the same, but for homotopies. So you have a boundary now going on. Okay, everyone ready? We can go? Okay, so we have phi in the kernel. And we want to show that it is a boundary. So what does it mean in the kernel? It means that this composite map here is null homotopic. Okay. Let us be a bit more explicit and make the map look more like a map that we constructed in the surjectivity proof. So choose an embedding of M into R M plus K. And now this map is obtained sigma K, sigma infinity S M plus K, mapping, new normal bundle. And we embed it into Rn plus K as some kind of tubular neighborhood. This maps sigma minus K, sigma infinity, ton of nu. And this maps to xi, but we can actually be a bit more precise. And actually I claim that I can get it psi for some m. And that's because, so where nu is f upper star psi km for some map m to b km. And that's because, nu was f upper star of psi for some map from m to b, but b is the colimit over km b km. And so we can factor it at some finite level since M is a closed manifold. And so in particular, it's a finite C-double complex. Actually, for smooth manifolds, it's easy to prove using triangulations, but we don't really need that M is a finite C-double complex, only that it is a retract of one, which is a lot easier to prove. So, in fact. Moreover, we can choose K big enough such that the composite Km is null homotopic. That's because if it's null homotopic in the colimit, it's null homotopic here for some finite K and M. And then you use Freudenthal as before, using the injectivity part of Freudenthal now. So again, this is compactness of Sm plus K plus Freudenthal.
Sorry, what's F here? Is it the map from M to BO?
Yeah, sorry. Well, I some map F from M to BKM that makes our composite factor like this. We know that it exists. I mean, we have a map which I called phi from M to B, and so it factors at some finite level, and I call the F this factorization. And sorry, and this is the map, the tomification of the map F. Which is the identity on every fiber. And this map, just since we're putting name, is the Kontriagin-Thom collapse map. That's the identity on nu and the base, everything else to the base point. Okay. Okay. Whew. Sorry, I went a bit quicker here since the argument is exactly the same as before, only with different bounds. But in any case, we take some very huge k so that everything works. And so we can extend it to dm. So we have, again, let me write it. This sits inside dm plus k plus 1. And we can extend this map like this, since it's null homotopic. And let me call this h. pt, and this is tom of f. Moreover, without loss of generality, we can ask that h is constant of rays for t greater than 1 minus epsilon x in the boundary. Well, greater or equal even. Not sure if we'll need the equal, but I mean, we can just, you know, it's continuous, so we can thicken it a little bit near the boundary. Okay, we're almost there. Now, remark. So, and oh, and remember, we have also this projection map here to eta km always. Well, I guess I should call it really the tomification of the projection. If I let P be the map from BKM to BOKM. Sorry, not BOKM, I'm calling it the Grassmannian KRM. So okay. Now the idea is as before. Actually, let me put the idea. Make the composed with H transverse to the Grassmannian KRM sitting inside the stomp space. And it's, as before, you need to be a bit careful because the stomp space is not a smooth manifold, although it's very close to one. And also you need to be a bit careful because you don't want this to screw up the boundary. So the first remark is that if you let A be the pairs, the objects Tx in the disk, such that T is, I don't know, 1 minus epsilon over 2, I don't care, something closer to the boundary, and X is in some close, in some, well, let's say in the unit disk of nu, or whatever, in some close neighborhood of the zero section of nu. Actually, let me say close neighborhood of zero section in nu. It's not very important. Then H restricted to A, sorry, this guy restricted to A is smooth and transverse to the Grassmannian. Because we know exactly what it is. it's oh yeah. After homotopying PF, so from M to the Grassmannian. Sorry, forgot this step is smooth. We can always make, I mean, this map is defined only up to homotopy anyway. So by the smooth approximation, we can choose that it is smooth. And this is literally just you take nu, you project it to the zero section, and then you apply this map PF. So this is extremely smooth. So as before, let U to be the pre-image of this psi km, and note that U intersects X such that the boundary is greater or equal than 1 minus epsilon is exactly nu times 1 minus epsilon by definition of the map. So we can find a homotopy of U relative to U intersect A such that, sorry, a homotopy of, I'm calling it, can I just call it PH? It's actually Tom P composed with H, but it's, well, okay. I guess I should be. Such that this map Tom P composed with H becomes smooth on U and transverse to the Grassmannian. Okay. As before. And now we have one. Because now you let W be the pre-image of the Grassmannian. This is a neat submanifold of dm plus k plus 1. Give boundary exactly m. Since we know what this map does on the boundary of dm plus k plus 1. And as before, Grassmannian km, this composite phi gives a psi structure on W compatible with the one on M. And that's the end of the proof. So the class of M is indeed a boundary. As you can see, it's exactly the same proof as before. We just need to be a bit careful with the boundary. Questions about this proof? I understand seeing it for the first time is a bit overwhelming, especially since I did the full general version that people typically do not do with a Xi structure hanging around. Typically, people do either the case when the Xi structure is the identity or is the map from BSO to O, or sometimes the map from the point to BO. And they don't do the general case. And both of these three cases are easier to explain typically. But since I was always confused by how the proof actually works for a general Xi structure, I wanted to give you the complete proof to show it's not really that hard. The only trick is that you have this guy, BKM, is not a smooth manifold anymore in general. So you have just to work with the transversality here. But that's not a problem. Okay. Questions?
So apart from this transversality on the Grassmannian, there are no new ingredients for the general case, right? Just some new notation.
There are no new ingredients, just working very carefully through the definitions.
Yeah. Okay, thanks.
But the transversality is important. As I said, in the topological case, I mean, it's the only place where we're really using that we have smooth manifolds. And it is typically what breaks when you try to do generalizations. I mean, it hasn't broken so far. Turns out that all the generalizations are true. But it's always the hard, making this transversality argument is always the nastier part of the thing. And while for smooth manifolds, it's actually relatively painless. It's essentially based on Sard's theorem, if you're familiar with it. But of course, for example, in the algebraic case, I have no idea how to even attack that for algebraic varieties. Okay, let me first tell you a generalization that I wish I could prove for you, but it's a major theorem. So we have this guy here, but we can do better. So remember, I define these as a group, but in fact, you can define it as an infinity space. So there exists an infinity category called psi n, whose objects are m-1 dimensional closed manifolds, and morphisms are Bordisms between them. Sorry, with Xi structure, i.e. a morphism from m phi to m prime phi prime is w phi tilde, such that the boundary is the difference between these two. These require some work to define. It's not that hard, actually, but I'm not going to do the technical work. That's not, I'm just going to give you a very sketch of this thing. And these has a symmetric modular structure given by this joint union of manifolds. I hope at least it is believable, this statement. So a morphism, it looks something like this. This is M, this is M prime, and this is W. And you can take this joint union. Then we can consider the space geometric realization of Cobb and Xi, which is the infinity groupoid obtained by inverting all arrows. If I have a category, I can get a groupoid by inverting all arrows. This is the same, also is true for infinity categories. So pi 0 of psi n is exactly omega minus 1 psi. And now this, since Cobb was an symmetric model category, this is just an E-infinity space. And therefore it's an E-infinity group, since we proved that this monoid is a group. And so instead of describing this as the homotopy group or something, we can try to describe this infinity space. And that's the following theorem by Galatius, Madsen, Tillman, Weiss. It's a very important theorem. Says that this is the one space of a certain Thom spectrum where MT psi is the Thom spectrum of the composite. Sorry, MT psi n. N is important. T psi n going from TBN to BON to BO, to spectra, and this is the one picking up the ON action on, and I'll be careful, not on the sphere, but on its dual. And the TBN, and I want to call this minus eta n, since it's essentially the opposite of the tautological bundle. TBN is just the pullback BON, BO, but this time I need a shift. And this, why am I saying this generalization? This is describing my O psi n minus 1 as pi minus 1 of a certain spectrum, which is different from the spectrum I described before. But if you look at the definition, it turns out that there's an n-connected map from sigma n mt psi n to to m psi, which is essentially the tomification of this vertical map here. So this recovers the Galatius, the Pontryagin-Thom theorem, but gives a much more explicit description. And the reason is, while the pi minus 1 of, the pi 0 of this infinity group is interesting, also the higher homotopy groups are interesting. They control the homotopy type of diffeomorphism groups of manifolds. So you can think of these as some kind of categorification. Instead of identifying this group as some kind of homotopy groups of M psi, you can identify the full infinity space of manifolds and cobordism as a certain spectrum that maps in a highly connected way to M psi.
I got a question.
Yes.
So this COP category, this COP n theta, it looks to me that already every morphism is invertible. I can just stick the opposite trousers. Ah, no, that's, yeah.
You don't get the identity, no.
Ah, that's not the identity. Ah, yeah, sure. Because, okay, yeah, it's not the trivial connection. Ah, okay, yeah.
This is exactly where the stabilization of the diffeomorphism group by connected sums show up. But okay, I am not an expert of this subject. I just wanted to mention it because it's a very, very important theorem. It's a relatively recent one, I think. The paper is, let me see. The paper is, it's not that long ago. It's 2010. So it's, and this, I mean, this builds up previous work over previous work, but it's a very convenient way of framing a lot of stability results. And also, I should probably mention that there is also a cobordism description of the higher spaces of this spectrum, omega infinity sigma k m t psi n, but it's more complicated and I don't want to state it here. You need to pick higher cobordism categories, which I don't want to define. Okay, so that was the supermodal observation. Let me go instead to the classical thing. I want to discuss why Tom proved this theorem and what he could do with it. There's the steam rod problem. Is it okay? Okay. So the steam rod problem is a very classical problem posed, I don't know, at the very beginning of algebraic topology when Poincare duality was proven, when the homology groups were proven. And it comes in two flavors, in the oriented and unoriented one. So recall, for any smooth and manifold M, there exists a fundamental class in H and M with coefficients in F2. And for every smooth, oriented, and manifold M, you can find a canonical integral lift. And I mean, it's traditionally not defined like that, but of course, in this class, we can define it as the composite of this, of the fundamental class this composite here, or HF2, if in the unoriented case. So the problem, so let X be a space, and any space, so let's do first the unoriented version, for which alpha in the mod 2 cohomology of X, there exists a map where M is a closed, smooth, and manifold, such that the push forward of the fundamental class is alpha. That seems a very natural question. And then you can do the oriented variant, which is for which alpha integral now, there exists a map. Now M is closed, oriented, smooth, and manifold. Such that f lower star of M is alpha. So this is a problem that I could have stated for you 1 year ago, perhaps, when you first saw the definition of fundamental class. And it was a problem posed by Steenrod. And the solution of this problem is essentially what moved Tom to prove his theorem. Is the statement of the theorem clear? Because now our goal is to represent this problem using more technology. So I claim, this is equivalent to describing the image of pi star MO tensor sigma infinity x plus and pi star and then the oriented one. Where MO to HF2 and MSO to HZ are the Tom classes. And moreover, actually are the, well, okay, I'll remark this later. Because remember, these groups on the left-hand sides are exactly groups of manifolds with a map to X, or respectively oriented manifolds with a map to X. So let's see what this map is. So suppose we have a manifold with a map to X. It's, let's say, M is N, for example. Then its class in pi star MO tensor sigma infinity of X plus is the composite. I think I wrote this very, very often. Yeah. Well, actually, I can realize it perhaps more explicitly as this, factoring like this, where this is the map we saw last time. It was the Pontryagin Tom of M inside M times M. It was called the Tom diagonal. Yeah. No, sorry, it's not the Pontryagin Tom, it's the induced map by the diagonal. Okay, but now we compose with the Tom class to HF2. And this is equivalent to composing with the Tom class there. But this is exactly if you recall, this is well, okay, no, sorry. I can sorry, and I want to claim that this composite here is exactly the same composite as I defined before to give the fundamental class, the image of the fundamental class. Sorry. And I want to claim that this composite here is exactly the fundamental class. But that's that follows immediately from the definition of the Thom isomorphism. It is brackets M by the Thom isomorphism. I mean, in the definition of the fundamental class, I use the Thom isomorphism. And if you look at how the Thom isomorphism works, it's exactly doing this.
Sorry, I'm a little confused just for the notation. So MO was what we called M psi before, but
oh yeah,
psi,
sorry,
the identity, right?
Yes, yes. I said it last time, but let me repeat it. M of the identity of BO and MSO is M of the map from BSO to BO. So let me repeat the notation, yeah. And okay, the same story works for MSO with the exact same diagram. Moreover, note that MO to HF2 and MSO to HZ are isomorphisms on pi naught. That's because the composite maps are Z subjects to F2 and Z goes to Z with the identity. Since by definition of Thom class. We want this map to correspond to the unit of this ring here. And so it's what it has to be. And then it's easy to see. Pi naught of MO is F2 because it's the Bordism of points. And pi naught of MSO is Z. Again, Bordism of oriented points. Or for MSO, you can actually use it also with Thom isomorphism. Oh, I'm out of time though. So let me just quickly say how you finish the steroid problem. So fact that I'm not going to prove, but that Thom proved, the map MO to HF2 has a section. And so pi star MO tensor sigma infinity x plus to pi star HF2 tensor sigma infinity x plus is always surjective. Okay, this is a bit hard to prove, but the next fact is going even easier to prove. MSO to HZ has a section rationally. And that's because every spectrum rationally is a sum of Hilbert-MacLane spectra. So this implies a partial solution to the Steenrod problem. So for every class alpha in H and XZ, there exists an n greater or equal than 1 and a manifold such that the push forward of n is n times alpha. In fact, a more refined study can show you that n can be chosen odd even, but that's not what we proved. Using the fact that mod 2 can always be realized. So the Steenrod problem is actually not true. Using similar methods, Tom showed that there are classes that are not in the image of the Bordism. But it is true up to integral multiples. And okay, sorry for going over time. I think I want to stop here. I think it's a cute application, especially since this actually we proved every single step here. We didn't prove this section, but this section rationally we proved. And so I wouldn't know how to prove these without using Tom spectra. I don't think anyone knows. But even if it's a very concrete problem about spaces and manifolds, you can see the power of this tool. Okay, I'll stop now. Okay.
I have maybe less of a question, but like a general question, general confusion maybe. So about this last fact, it's clearly important, as you say, but for some reason it seems that we've used something very, very advanced technically, and then we reduced everything to rational numbers where kind of much of our machinery actually trivializes. So I'm a bit lost about.
Well, the hard fact that I'm using here is the Pontryagin-Thom theorem. Here, where is it? Here, the very beginning. This theorem here, the Pontryagin-Thom theorem, and I don't think it would be easier to prove rationally. Of course, the fact that we have these fancy integral statements allow us to do a more refined study. For example, you can construct a whole obstruction theory, or you can actually ask, okay, but what if I allow some singularities on my manifold?
Mm-hmm.
And it turns out that you can, for example, you can realize every class if you allow singularities in codimension on at least 5, I think. That also will follow relatively easily from what we did so far. And then you can ask, okay, but what if I don't want to allow singularities in codimension 5? What if I allow singularities only in codimension 8? And then you can see that they're using the homotopy type of this spectral MSO. You can see there is exactly one obstruction, and you can find exactly what conditions you have on your integral homology classes to be realized in codimension 8. And in fact, it's how Tom proved that the Steenrod problem does not always have an affirmative answer by showing some class for which this obstruction does not vanish, in fact. So, in fact, the reason why it seems like we're using a lot of advanced techniques is that I just did the simplest possible case here, which is basically gets crushed by our machinery. But still, even for this simple case, I do not know of a more elementary proof. I mean, you can phrase it not in terms of spectra, which didn't exist at Tom's time, but in terms of Tom spaces, and filter colimits of stable homotopy groups of Tom spaces. But it's not clear to me that it would obviously be easier.
I see. Okay, wait, and you've mentioned this codimension 5 and 8. So this means that for a low n, does it have like always a solution?
Yeah, there is this cute little fact that the homotopy groups of of the Postnikov tower of this guy, less or equal than m, is Bordism classes of objects with singularities in codimension m+1. I don't want to make it precise what I mean per objects with singularities. If you want a reference, these are called stratifolds, but
okay.
And so in particular, you can see that integral classes are Bordism classes of objects with arbitrary singularities and codimension at least one. Since Hz is exactly the zero truncation of MSO. And this is analog, I mean, I'm telling it mainly for you, this is an analogous of the fact that multivic homology can be realized as some sort of Chow groups, where the cycles can have arbitrary singularities.
Okay.
And yeah.
That last sentence was highly interesting indeed, but I should digest it, so maybe.
Yeah, I mean, it's not a completely, I mean, the kind of objects you're working with are very, very different. The stratifolds do not behave so really like algebraic varieties. So analogy is not perfect, but there is a story here. Actually, by the way, I discovered this particular fact like 2 days ago preparing this class. So it's not like I'm an expert, but I think it's a very cute fact. And this fact I actually knew already. And the proof is actually not that hard. Once you have this Pontryagin-Thom theorem, you have just to set up the definitions of these objects with singularities, and you can get these as a corollary, essentially.
Oh, I see. So somehow you don't even need to perform the proof once again.
No. You can. Essentially, what you have to show is that the Bordism classes of objects with singularities is a homology theory. And of course, it has a map from the homology theory given by M psi, because manifolds are, in particular, have singularity in codimension greater or equal than n+1. And then you can just check that it's on a level of homotopy groups. It is an iso in dimension from n downwards, and it's a 0 upwards, and you're done.
I see.
It's a very cute proof. I like it. Of course, you have to spend some work in setting up the theory of these objects with singularities instead.
Yeah. Or at least believe in the existence of such. Yeah. Okay, thanks.
Let me stop the recording.